In a quiet lab, scientists were tracking light. Nothing unusual, just beams crossing, interfering, behaving exactly as physics predicts. Then something strange appeared. Tiny pinpricks of darkness began forming inside the light itself, like shadows twisting and sliding through the beam. And when researchers followed their motion, the data didn't make sense. These dark spots weren't just moving, they were racing ahead, faster than light. For a moment, it looked like one of the universe's most unbreakable rules had just been challenged. So what did they actually see? What scientists observed wasn't a particle, but a precise point where light completely vanished. In the experiment highlighted in recent reports, physicists used carefully controlled laser beams to create complex interference patterns, regions where waves overlap and either amplify or cancel each other. At specific points, the light waves canceled perfectly, creating tiny zeros of intensity known as optical vortices, or, more visually, pinpricks of darkness embedded within the light itself. Using high-speed, high-resolution imaging techniques, researchers tracked how these dark points moved as the surrounding light waves evolved. What made the observation remarkable was not just their motion, but their speed. These points appeared to sweep through the light field faster than the light waves themselves. That's the moment the experiment crossed from expected physics into something far more intriguing. The evidence wasn't theoretical speculation, it was directly measured. The setup allowed scientists to map the structure of the wave in real time, following the exact position of these dark singularities as they shifted. And importantly, their motion wasn't random or chaotic. It followed consistent mathematical rules tied to the geometry of wave interference. That consistency is what convinced researchers they were seeing a real, reproducible phenomenon. The key to understanding this lies in recognizing what these dark points actually are. They are not objects, particles, or anything that exists independently. Instead, they are defined by the structure of the wave itself. When waves overlap in certain ways, they create stable points of cancellation. These points can move as the wave evolves, but they don't carry energy or substance in the traditional sense. This distinction creates a fascinating tension. If something can be tracked, measured, and predicted, we naturally think of it as real. But here, what's being tracked is an absence, a location where something isn't, and yet that absence behaves in a way that seems to defy expectations. So the real mystery isn't just that something appears to move faster than light, it's that what's moving isn't something at all in the traditional sense. And that raises the next question. If it's not a physical thing, how can it move this way? The answer lies in a subtle but powerful idea. Not everything that appears to move is actually traveling through space. These dark points are not objects, they are patterns, and patterns follow a completely different set of rules than physical matter or energy. To see this more clearly, imagine sweeping a laser pointer across a distant wall. If you move your hand quickly enough, the dot of light can jump across the surface at incredible speed, even faster than light would take to travel between those points. But nothing physical is making that journey. Each position of the dot is created by new photons arriving from the source. The motion you see is a pattern, not a traveling object. In the experiment, something similar is happening, but on a much more complex level. Light behaves as a wave, and when multiple waves interact, they create intricate interference patterns. Within these patterns are regions of brightness and complete darkness. The dark points exist only because of how the waves cancel each other at that exact location. As the waves evolve, shifting phase, interacting, and reconfiguring, the positions of these cancellation points also shift. Under certain conditions, the geometry of the wave allows these points to move extremely fast. The speed comes not from something traveling, but from the way the structure of the wave reorganizes itself. This is why the observation doesn't conflict with the known speed limit of the universe. That limit applies to anything carrying energy or information from one place to another. These dark points do neither. They don't transmit signals, they don't push or interact with other objects. They are simply markers of where the wave cancels itself out. Physicists describe this using concepts like phase velocity and interference dynamics. In many wave systems, the shape of the wave can move faster than the underlying medium. The peaks, troughs, or cancellation points can shift rapidly without anything physical exceeding the speed limit. What makes this case special is how clearly it was observed and measured. It turns an abstract concept into something tangible, something you can track and analyze. And once you accept that patterns can behave this way, it changes how you think about motion itself. Because now, the question isn't just how fast things can move, it's how fast structures can evolve. And that opens the door to something much bigger. This discovery matters because it confirms a prediction that has existed in physics for decades but has rarely been observed so directly. The mathematics of wave behavior has long suggested that certain features, like these dark singularities, could move in ways that appear faster than light. Now, with modern experimental tools, scientists have finally captured that behavior in action. The practical impact begins in fields like photonics, where understanding how light behaves at extremely small scales is essential. By tracking these fast-moving patterns, researchers gain new insight into how waves evolve over time. This can improve technologies that rely on precise control of light, from advanced imaging systems to high-speed optical communication. In quantum physics, where wave behavior dominates, these findings offer another layer of understanding. Many quantum systems are described by wave-like equations, and being able to observe and interpret complex wave structures could help scientists study interactions that are otherwise difficult to detect. In this sense, these dark points become tools, not because of what they are, but because of what they reveal. There's also a broader conceptual shift happening here. Traditionally, physics focuses on objects, particles, forces, energy. But this experiment highlights the importance of structures. The behavior we observed wasn't about something moving through space, but about how a system reorganizes itself over time. That perspective has deep implications. It suggests that some of the limits we think of as absolute are actually more specific than they appear. The speed of light remains a fundamental boundary, but only for certain kinds of motion. Outside that category, other forms of behavior can emerge that don't fit our usual intuition. What makes this especially fascinating is that the fastest thing in this experiment isn't something you can touch, measure directly, or even define as an object. It's a point of complete absence, a place where light cancels itself out entirely. And yet, that absence follows precise rules, moves in measurable ways, and reveals new layers of physical reality. This shifts the narrative from breaking limits to understanding them more deeply. It shows that physics isn't just about what exists, it's also about how existence is structured. And sometimes, the most revealing discoveries come from studying the spaces in between. What makes this discovery so powerful is not just what it shows, but what it questions. These experiments aren't just tracking strange patterns in light. They're exposing how limited our intuition is when it comes to motion, speed, and the structure of reality itself. And that's what makes this moment so exciting. Because every time we think we've reached a fundamental limit, physics finds a way to reveal something deeper hiding beneath it. So here's the real question. Are the limits we trust truly absolute? Or are they just part of a much bigger framework we're only beginning to understand? Drop your thoughts in the comments. I'm genuinely curious. If you enjoyed this video, don't forget to like, share, and subscribe for more updates on space exploration and scientific discoveries. Your support truly makes a difference and helps this channel grow. Thank you for watching, and see you next time.